Hey guys, today we're going to be doing an induction question. We're going to be proving this thing, and we'll involve some tricks and some trig identities. Start off, base case n equals 1. The left-hand side equals inverse tan 1 on 2 times 1 squared, which is just inverse tan a half. Right-hand side is pi on 4 minus inverse tan 1 on 2 times 1 plus 1, which is equal to pi on 4 minus inverse tan a third. Now, we want to show that this is equal to this, but we need a way to compare them. So what we can do, we can take tan of the left-hand side is equal to a half, because the tan and the inverse tan cancel out. Then tan right-hand side equals tan pi on 4 minus inverse tan a third, and we can use our tan a minus b formula, tan a minus tan b over 1 plus tan a tan b. That should be a pi on 4, and that's equal to 1 minus a third over 1 plus a third is equal to a half. Therefore, tan left-hand side equals tan right-hand side. So this is good. This is a good start, but the problem here is that this does not yet imply that left-hand side equals right-hand side. And as a counterexample, I'd say that tan 0 equals tan pi equals 0, which obviously does not imply that 0 equals pi. That would be wrong. So we're going to have to do a bit more work. Now the observation here is that, I'll draw the axes up, if the left-hand side and the right-hand side are between minus pi on 2 and pi on 2, then tan left-hand side equals tan right-hand side will imply that they're equal. I'll show you. That's the graph of tan x. This is pi on 2. That's minus pi on 2. Notice for, say, minus pi on 2 x to pi on 2, tan x is injective. This means for every x value, there is one y value, and for every one y value, there is one x value. It's this one-to-one correspondence. We say it's injective. Therefore, if minus pi on 2 is less than left-hand side and right-hand side, and that's less than pi on 2, and tan left-hand side equals tan right-hand side, this implies that the left-hand side equals the right-hand side because of that injectivity I was talking about. So now we just have to show this thing. So what we can do is we can take a look at the graph of inverse tan. I'll do the asymptotes in orange again. That's at pi on 2 and minus pi on 2. And this is a half, and that's inverse tan of a half. So you can clearly see that minus pi on 2 is less than inverse tan a half, is less than pi on 2. And that's just equal to the left-hand side. So that's good. Now the right-hand side is a bit more complicated. Recall that right-hand side is pi on 4 minus inverse tan a third. But that's all right. We can still work with that. So by the same logic, using the graph, we have minus pi on 2 is less than inverse tan a third, less than pi on 2. So we'll just rearrange this a little. We'll start by making everything negative. And we have to flip our inequality signs when we do that, of course. And then we can just maybe, you know what, I tell you what, we can even say that 0 is less than inverse tan a third is less than pi on 2. You can see that from the graph, it's greater than 0 there. Which means that 0 is greater than inverse tan a third. It's greater than minus pi on 2. We'll add pi on 4. So you can clearly see that. Whoops. Oh my god. So many errors. So many errors. Right. Okay. So the right-hand side is a bit more complicated because, as you can recall, right-hand side is pi on 4 minus inverse tan a third. So we'll start with our inverse tan a third. We can actually see that 0 is less than inverse tan of a third. It's less than pi on 2. You can see that it's positive. So we'll flip this around because we want this to be negative. Eek. And then we can just add pi on 4. Note that that thing becomes the right-hand side. Therefore, if that's true, then this is clearly true. And that's what we wanted to show. So, eek. Therefore, since minus pi on 2 is less than left-hand side, right-hand side is less than pi on 2, and tan LHS equals tan right-hand side, this implies that left-hand side equals right-hand side, which is what we want. That's our base case done. So that's a bit more effort than you normally put in, but I wanted to prove everything as rigorously as I could there. Okay, right, time for the inductive step. We will assume that inverse tan 1 on 2 times 1 squared plus blah 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 plus inverse tan 1 on 2k squared is equal to pi on 4 minus inverse tan 1 on 2k plus 1. Now, for n equals k plus 1, we'll prove the left-hand side equals the right-hand side. So the left-hand side is equal to this. We just add one more term onto it. And notice that since this is equal to this, which is equal to that, we can just sub that in for there. So we'll say that it equals pi on 4 minus inverse tan 1 on 2k plus 1 plus inverse tan 1 on 2k plus 1 squared. From assumption, got to write that. Now, remember that we want this to equal pi on 4 minus inverse tan 1 on 2k plus 1 plus 1. It's important we don't lose sight of that. And in fact, this bottom can actually just be written as 1 on 2k plus 3. So we need a way of getting these two inverse tans and making them into one thing. So we'll use another less so common trig identity. Let's say we've got tan A minus tan inverse A minus tan inverse B, and we want to simplify that, so we'll call it X. Then we'll just call it X, and then we can take tan of both sides, and we'll have A minus B over 1 plus AB equals X. Therefore, X equals inverse tan A minus B over 1 plus AB. So, in this case, our A is equal to this thing, and our B is equal to that thing. So we'll just plop that in our identity. So that's pi on 4 plus inverse tan. I'll do big square brackets. 1 on 2, k plus 1 squared minus 1 on 2, k plus 1 over 1 plus 1 on 2k plus 1 squared 2k plus 1. Now, remember, we want to show that it's pi on 4 minus this. So we want this plus sign to be a minus sign. And we can do that by using the fact that inverse tan is an odd function. So it's got that, nice symmetry, which means that f of minus x equals minus f of x. Because that's a property of odd functions, and inverse tan is an odd function. So that means this is still left-hand side is equal to pi on 4 minus inverse tan, and we have to make the inside negative now. So we've made it negative, denominator remains the same. And then we can just multiply the top and the bottom by this boy, simplify everything down a bit. So we'll have 2k plus 1 squared minus 2k plus 1 over 2k plus 1 squared 2k minus 1 plus 1 plus 1. I'll expand the top. I'll just Control Z that. And the bottom. Now, to expand this cubic, we could just write it all out and then collect like terms, but there is an easier way to do that. We know that this thing's going to be a cubic, so we can just work out the coefficient of each term in that cubic. So the first term is 4k cubed. That will be 4k cubed. Then for the k squared, we have 2 times 1. Remember that, 2 times 1, and 4 times 2. And those are the only ways to get k squared. So 2 times 1 plus 4 times 2 is equal to 10. So I have a 10k squared. Then we'll have our linear, so that's 4 times 1 plus 2 times 2. We have 4 times 1 plus 2 times 2, and that's equal to 8. So we'll have an 8k. And then we have 2 times 1 plus 1 is 3. So, and recall, we want all of that to just equal 1 on 2k plus 3. So we're going to have to do some factorization here, but it means we're going to have to factorize this cubic, which could be tricky. However, when things are tricky, you always use a trick. So what you've got to recall is that we know that this thing has to equal 1 on 2k plus 3, which means that there's really only one way this cubic can factorize. It has to factorize like this in order to cancel the denominator. Right, this is what it has to be in order to cancel out the denominator. So we can then go and verify if this works by expanding the same way we did before. That's 4k cubed. So far, so good. We've got 2 times 3 plus 2 times 2. 2 times 3 plus 2 times 2 equals 10. Plus 10k squared. Still looking good. We've got the linears 2k, 2 times 3 plus 1 times 2. 2 times 3 plus 1 times 2 equals 8. So we've got an 8k, and then the last term, 1 times 3 is 3. And that's what this equals. So that's good. So that means our expansion or our factorization was correct. So we can use that trick because we know what it has to equal ahead of time for the induction to even work. And I'll just rewrite the 2k plus 3 as 2k plus 1 equals pi and 4 minus tan inverse 1 on 2n plus 1, where n equals k plus 1. And that is what we wanted to prove. So the induction's done. We just need a concluding statement. Really depends how anal your teachers are about this, but the safest option would be to write something like this. Holds for k plus 1 if it holds for k. Since it holds for 1, holds for 2. Since it holds for 2, it holds for 3, and so on. Therefore, statement holds for all positive integers by mathematical induction. Hooray! So there is the proof. All done.